I'll be chairing this session 3B. And in this session, we are going to have one invited talk followed by 4 other presentations. First of all, I'd like to brief the invited speaker of the day. Dr. Ileana Wuhan is an assistant professor of cryptographic engineering in the Digital Security Group. Her research interest focuses on developing tools to help designers of cryptographic algorithms develop secure implementation. She has spent over 10 years in the security evaluation industry while at Riscure. She serves on several program committees of conferences that specialize on hardware security. Techies, COSADE, CARDIS, FDDT, DATE, SPACE, and many more. She has also been appointed General Chair for CHES 2018 and Program Co-Chair for CARDIS 2022. Today, she is going to talk upon cryptographic issues in hardware. The title is Dream or Reality? Automated Prediction of Cryptographic Vulnerabilities During Hardware Design. Now, given the threat of side channel analysis, leakage assessment of the chip is very important for the semiconductor industry and has received a lot of attention in the recent years. So she has done a lot of studies on these topics, and today she is going to present the various thought process to prevent this hardware from these kind of attacks. So now I invite Dr. Ileana Wuhan to start her talk.
So in this talk, we're going to explore whether the automated prediction of cryptographic vulnerabilities is a dream or a reality already. When discussing cryptographic implementations, we typically deal with 2 types of implementations, software and hardware implementations. With the current state of the art, the main question is not if an implementation can be broken, but how much an attack would cost. Our measures for the success of an attack estimate the effort required for breaking an implementation in terms of cost of equipment, computation time, human and machine effort. The distinction between software and hardware implementation is important. If a software implementation is found to be vulnerable to an attack, its implementation can be fixed anytime by adding countermeasures. However, if a hardware implementation is found to be vulnerable, its implementation cannot be fixed after tape-out. All things being equal, it's true that the hardware implementation is more difficult to break because it may require a non-standard leakage model and definitely more traces. There are 2 approaches when it comes to automated vulnerability prediction. The first is formal verification, where formal proofs are given about the security of a cryptographic implementation. The proofs check the vulnerability of the implementation against a simple and abstract adversary, such as the deep probing adversary, who can place up to deep probes on freely chosen spots to record noise-free and stable signals. The verification is exhaustive, checking all possible combinations, and there are no false positives. However, the price to pay for these conservative evaluations is the possibility to only verify relatively small circuits. Think of round size for a symmetric cryptographic implementation. The other option is to experimentally prove the security of a device using leakage simulators. And the tools in this category aim to mimic the behavior of the device once it is fabricated, in order to predict the results of leakage assessment on the fabricated prototype. Adversary gets access to realistic power consumption of the device, which aims to strike a balance between precision and speed. False positive will be present, however, such tools can verify large circuits. Leakage simulators, which are the main topic of this talk because of their capabilities, aim to detect leakage in traces by generating a set of simulated traces and then applying a leakage detection method, such as test vector leakage assessment or TVLA. Simulation of traces can be done with tools such as the Synopsys Prime Time PX. Generating realistic simulated traces depends on the amount of information available about the target and device, and also about which abstraction layer we are simulating. Once the leaks have been identified, a human expert can take over and fix them, or they can be automatically patched. Here is an example of leakage prediction for the first round of an AES SBox implementation running on a RISC-V processor. We draw horizontal lines at the threshold of plus minus 4.5. If a point exceeds the threshold, we can conclude with 99.99% confidence that our fixed run can be distinguished from the mean and our random set. Therefore, a DPA attack is likely to succeed. To determine if there is data dependence in the power consumed by the target, we create two sets of traces. One where the input data is fixed and one where the input data is random, the encryption key being the same for both sets. For each cycle, we compute the t-scores between the fixed and the random set. And an important note is that due to the hypothesis testing's intrinsic nature, it is only possible to confirm the leaks present, but not its absence. Before moving further, let's have a look at how side channel leakage is captured at different abstraction levels. At the lowest level, the place and route, when all connections between the cells have been established, the data is represented as voltage moving through the different components. The power model when we have access to commercial simulations tool, which estimates the power in watts using differential equations. And the power consumption is very high. However, as each individual transistor is modeled independently, this takes a lot of time. At the logic level, we have access to the chip layout, the data is modeled as bits. The basis for the power consumption is a netlist of the cells of the circuit. The netlist contains all the cells and the connection between the cells. Power simulation is done in two steps. The first is to simulate which transitions occur at which cells and at what time. The second step is to map the transitions to a power or a toggle trace using a power model function. The result of the simulation at this level is a toggle trace, which records the activity of each cell using discrete values. At behavioral level, power simulations are very fast, but typically imprecise. At this level, we have a high-level description of the components in the circuit, memories, microcontrollers, etc., and high-level power models for these components. For simulation related to side channel attacks, we are only interested in the power consumption related to the data transition and the data-dependent operations. We see here a list of available tools for pre-silicon leakage simulation. We classify these tools according to the abstraction level: behavioral, ISA or RTL, logical or gate, and analog or layout. We also consider what the end device is and the target implementation that has been tested with these tools. And the end device tells us what type of implementation has been verified with these tools. There are two ways to determine the power consumption of a device, as we said before. The first is simulation, where the power consumption is generated with a commercially available tool. And the second is estimation, where the power consumption is estimating using a custom defined function. The exceptions to this are Coco and Script, which are using checkers to verify the secure run of the target algorithm in the end device. Finally, the columns of detect, verify, and mitigate tell us about the capability of the tools. Detect means that the tool is capable to detect leakage. Verify means that the tool is able to determine what caused the leakage, and mitigate means that the tool is able to automatically patch the leakage. Open source specify whether this tool is available as in the open source. An example that we will look at is COCO, a gate level tool, which it was run on a RISC-V device and can check software implementations. The original publication of COCO reports results on an EBEX score, which is a small RISC-V implementation of about 27 gates. And a more recent publication from the same authors showed the tool in action for a large core of approximately 420K gates. For comparison, I selected the results reported on the second order implementation of a DOM SBox, or domain-oriented masked SBox, which is reported to take 3 minutes on the EBEX score and 1.3 hours on the SWE RV core. Let's also look at Karna, which is a tool which operates at the layout level and which has been used to verify AES and Simon and present cores. And they use commercially available tools for simulation. This tool is able to automatically patch vulnerable gates. Karna, as I said, was evaluated in 3 different open source cores, and the first is a bit serial implementation of the Simon block cipher. This is a small design of approximately 622 gates, and this analysis with Karna takes approximately 6 hours. The netlist is synthesized at 28 nanometer cell size. The second is a present core. We don't have precise information about the size, but we know that it's in the same range as Simon from the time it takes to do the analysis. The third one is an optimized AES. Again, we don't have precise information about the area, but we know that this design can be 80% larger compared to Simon, and it takes about 3 days to do a full analysis. And compared to the unoptimized AES design, where the results are shown to reveal the correct key byte at approximately 2,000 traces, Karna can achieve a user-specified security level in all 3 designs with no impact on the delay or the number of gates, but pays a price of 20% increase in the utilization area. The authors report that 96% of the processing time for Karna is spent on generating these power traces that are required for the analysis. To conclude, I have here a picture which shows a sort of history of attempts to create leakage simulators. And we see that while it starts rather slow in 2003, 2004, the efforts in creating such tools have intensified in the last few years. We don't necessarily conclude from these tools that from the abundance of these tools, that we now have a solution or a generic solution that would work in all scenarios, because the tools aim to solve very specific use cases. But we see that with the increased number of proposals, it might be easier to identify the best tools for the best use case. So to conclude and to revisit the question at the beginning of the presentation, is it a dream or a reality, the possibility to verify, to automatically verify traces? My conclusion is, or my answer to this question is, it was a dream, which is now becoming a reality. Thank you.
Thank you, Liana. It had been a very good insight into the topic, and you beautifully articulated the role of leakage into the hardware design for cryptographic applications. And it's very important. I do understand, and I second it, that it is very, very important. So I was just wondering few things. Maybe I'll put up 1 or 2 questions. Like you have been talking about various architectures, various algorithms into your presentation. So, like every algorithm, you must be getting a different leakage. Okay, so every kind of hardware which you choose or the architecture you choose for the implementation, your attacks are dependent on the architecture chosen as well, or on
Yes.
algorithm only?
So thank you for this question. Typically with side channel attacks, we attack variables which come as a result of a nonlinear functions. So the target is typically nonlinear functions, and of course, different algorithms, different target intermediates. What is crucial for the success of an attack is how well we get the leakage, how right we get the leakage model. In some cases, we know of some generic leakage models, such as the Hemingway, the identity model, but for very precise evaluations, because we are not always interested in an attack, we also want to find out what is the cause of a leak. We want to model the hardware as precisely as possible. And it has been shown that microarchitecture implementation is a crucial aspect of getting the leakage model correct. Does that answer your question? Yeah.
I was having another question. Today I keep hearing that people are going in for lightweight kind of solutions or cryptographic algorithms. So do they have more leakage or something like that, or it can be anything?
I'm sorry. So the question was about lightweight crypto, and
Yeah, yeah.
I didn't hear the question.
My question was, today people are going in for lightweight cryptographic algorithms. So do they get less leakage over there or high leakage over there, or there is any functionality or relationship between two things? Can anything be predicted over it, or one has to evaluate only and then you can say?
Yeah, so as in any algorithms, we have multiple protection layers when it comes to side channel analysis, right? So at silicon level or at transistor level, we talk about, for example, different types of circuits. So we have something that is called a dual rail circuit, which balances the consumption of power when different bits are being consumed. At higher level, we have things like mask gates. Even higher, we know about like an algorithmic level implementation or countermeasures such as masking. We know about hiding signal. So as in with any other algorithms, yes, we can protect them. But with lightweight, we want to make sure that the protection is as effective as possible. And we are now, at the lab where I am, we are participating in a NIST evaluation of all the lightweight candidates with respect to resilience to side channels. Does that answer your question?
Yeah, yeah. Thank you for giving me insight into it. Thank you so much. It had been
Thank you for the invitation.
So next talk is an attack resilient PUF-based authentication mechanism for distributed systems. And the speakers are Mohammad Ibrahim Badi, Mohammad Yunus, Wasila Launani, and Nagme Karimi. They are all from University of Maryland, Baltimore country. So now I invite them to present their paper.
Hello everyone, I am Mohammad Ibrahim Abadi, and today I am presenting our paper titled as an attack resilient PUF-based authentication mechanism for distributed system. This is a joint work between me and my collaborators, Dr. Mohammad Yunus, Wasila Lalwani, and Dr. Nagme Karimi. This is the outline of my presentation. I first go through introduction, then we have a brief explanation on PUF. We will talk about our threat model. We propose our PUF-based authentication scheme, and finally, we will have experimental results and conclusion. With the rapid expansion of IoT network in so many applications such as home automation, smart transportation, power grid, and healthcare, providing the security for this network is a major challenge. For example, if an attacker hacks into an IoT network, he or she may compromise the network functionality. Later, we may have failure in our IoT network. Therefore, we need to ensure the security of IoT and the authenticity of device in IoT network. To preserve the security, IoT needs should be authenticated frequently. This is the basic idea of authentication. For example, the server wants to authenticate this IC, server sends a random number, IC will encrypt it with private key and send it back to the server. Server will decrypt the received number with the public key of the IC, and finally, server can authenticate this IC. There are two possible strategies for authentication in IoT networks. The first one is symmetric key crypto-based authentication. However, it has high overhead key management protocol. The second one is the asymmetric key crypto-based authentication. It also has high computational overhead. Therefore, we need a low-cost secure authentication solution. There are two forms of managing IoT networks: centralized one and distributed one. In the centralized network, server controls the communication between pair of nodes by authenticating each node. However, it has some challenges. Any failure in server will shut down the entire network. Also, high traffic downgrades the performance of centralized network. Availability of the server is not always guaranteed. Therefore, we need to move toward distributed network. In distributed management network, each node is able to authenticate another node before starting communication. We target distributed control IoT network and design a hardware-based authentication protocol for this network. In our design, we use physically unclonable function. What is POF? Actually, POF is a hardware implementation of a one-way function, which is as a result of process variation during manufacturing the circuit. And also POF generates a unique signature for the circuit, which is related to its input, which is called challenge, and its output, which is called response. POF needs to be unclonable, unpredictable, and reliable. The POF-based authentication algorithm mainly consists of two phases: enrollment phase and verifying phase. In the enrollment phase, we need to generate a list of challenges and then query the POF with that challenges and record the response of the POF. Later in the verifying phase, we query the POF with one of the challenges, and then we receive the POF response and compare it with pre-stored response from the memory. However, POF has a main shortcoming, and it is its vulnerability to modeling attack. When the POF behavior is modelable with the machine learning algorithm. For example, for a 64-bit arbiter POF, you can model the POF with accuracy of 90% if you have 500 challenge response. Therefore, we need a modeling resilient authentication methodology. So this is our threat model in this research. So here we assume that this node NJ wants to authenticate the NI. This node send the challenge and receive the response. Here the adversary is able to intercept the communication traffic of the communication link between these two nodes and use the captured challenge response to build the machine learning. However, this attacker is able to reverse engineering the chip. It means that he or she has access to the implemented algorithm inside the IoT device. Also, the attacker is able to capture device to query its embedded POF. Our solution here is applying challenge obfuscation, which is resilient against reverse engineering, modeling attacks, and impersonation. In sum, our contribution is devising an effective POF-based distributed authentication protocol while safeguarding against POF modeling attacks through collusive group of malicious nodes, developing an approach for node and packet-specific challenge obfuscation toward modeling attacks targeting the embedded POF, and finally, analyzing the resiliency of proposed method against different attack scenarios. In particular cases where the adversary eavesdrops on communication links to intercept transmission. So before presenting our scheme, let's see that what is the challenge obfuscation or scrambling. Actually, it's a simple scrambling. It means that the challenge bits are reordered. So here, if you consider that the C is the query challenge, in the regular using of the POF, the C0 is connected to the first multiplexer and C63 is connected to the last multiplexer. But in the obfuscation scheme, we have a light circuit here to scramble these challenge bits or shuffle these challenges. You can see that instead of C0 right now, the C12 is connected to the first multiplexer, and instead of C63, C9 is connected to the multiplexer. The goal behind the obfuscation is that we want to hide the relation of the query challenge and the response of the POF against modeling attack. This is the main hardware block diagram of our proposed algorithm. So let's see a step by step about the process inside this algorithm. First, the query packet is received and verifier ID and challenge is extracted. Based on the PG block or pattern generator, we generate a muted challenge, which is the concatenation of the ID and some part of the challenge. Here, the mode is switched to the 0. Therefore, this line is routed to the POF. Muted challenge is applied to the POF, and the response is stored in this shift register. We repeat another iteration. In the next iteration, the muted challenge is shifted to the left, and again, it's applied to the POF, and another response is stored in the shift register. We repeat this iteration till this shift register is loaded completely. This shift register is used as a seed for this LFSR that later is used for scramble. Okay. In the next stage, we switch to mode 1. The first output of the LFSR come out, so it is 12. It means that the first bit instead of C0 should be C12. In the next tab, we have 48 and C48 come out of the scramble, and finally C9. So as the mode is 1, this challenge is applied to the POF, and the corresponding response is sent back to device. I mean that the verifier. This algorithm has two main advantages. The first one is that the challenge scrambling is node specific. If the verifier is changed, the scrambling pattern is changed as well. Challenge scrambling is challenge specific as well. For example, the scrambling pattern will be changed for the next query of the verifier. Before presenting our experimental result, see that what is our experimental setup. We implemented our proposed algorithm, including 64-bit arbiter POF, LFSR, scrambler, and all other components in Xilinx RTX7 FPGA. We also use logistic regression support vector machine and neural network for modeling attack. So here we want to show the efficiency of scramble. So here you can see the attacker goal is modeling the POF embedded in NT. Actually, NT is the prover node, and the N1 till N5 are verifiers. So attacker eavesdrop one of the links between NT and N1 till N5. You can see here that without our proposed authentication scheme, the accuracy is at around 90%. When we increase the train size, it scales at around 99%. With our proposed algorithm, you can see the accuracy is fluctuating at around 50%. Therefore, we can mitigate modeling attack. In the first attack scenario, we consider that the adversary intercept one of the communication links between verifiers and prover. And later, he wants to build a machine learning model based on what he or she intercepted to predict the other links traffic. You can see here, for example, by intercepting the first link, the attacker cannot model the response of the other link. As you can see that the accuracy is at around 50%. For the all other cases, again, we have the same result as the accuracy is at around 50%. Therefore, intercepting all traffic of one link cannot be helpful to model other links. In the second attack scenario, we consider colluding of two communication links to model other links. Here, for example, adversary collude these two links to predict these three links. You can see here that the attacker adversary is at around 50%. For all other scenario, for example, colluding link 1 and 3, you can see that against the attacker accuracy is at around 50%. Therefore, by colluding two links, attacker cannot model other links. In the third and the last attack scenario, we consider that attacker can collude a portion of all communication links to model the response of the unseen challenges. For example, here, attacker eavesdrop 10% of all link here, and then he or she build a machine learning model to predict the rest of 90%. As you can see, the accuracy is still at around 50%. Even if by increasing the portion of the colluding to 50%, he or she cannot have a good accuracy. Also, we evaluate our proposed authentication scheme against other algorithms. You can see that SVM, logistic regression, and neural network also cannot be helpful to model the path embedded in node NT, and the accuracy is at around 50%. So our proposed authentication scheme can tackle the contemporary attack in IoT network. For example, we can mitigate impersonation and civil attack. Definition of the impersonation and civil attack is in this way, that when a malicious node identified itself as a one-off or multiple IoT node in the network. So as the adversary does not have the same path and also is unable to model the targeted path, he or she cannot launch this attack. We are safe against reverse engineering attack because the scrambling pattern is unique and unpredictable for each device. If the attacker is aware of the scrambling algorithm to launch modeling attack with M challenge, she or he needs to try 64 to the M possible combination to model the path. In that case, we are safe against brute forcing attack. So, what is our system overhead and noise? You can see that the required memory for each IoT device to store the challenge response is based on this equation. Ti is the time interval of enrollment, AR is authentication rate, ND is the number of devices in IoT network, N and R is the size of challenge and response. In case of the area overhead, we have one LFSR, it includes 6 DSS and 1 XOR gate, 1 shift register, 1 multiplexer, 1 demultiplexer, and a very small state machine. We have 6 clock cycles for seed and 63 clock cycles for calculating scrambling. And also in case of the power, we have a negligible power overhead. We will mitigate the transmission noise to protocol level, and the noise of the path is mitigated via multiple measurement and majority voting. Then, in this research, we propose the robust modeling resilient path-based authentication for distributed IoT network. The proposed scheme is based on challenge obfuscation, which is node and challenge specific. The proposed method can prevent the contemporary attack in IoT networks, such as impersonation, civil attack, and also it is robust against reverse engineering and brute forcing attack. We will investigate the possibility of validating the data integrity of transferred message between IoT device in distributed IoT frameworks in the near future. Please feel free to leave your question in my email. Thank you for your attention.
Thank you, Mohammed. It had been a wonderful talk from you. Good work done in the paper. I was just wondering 1 or 2 questions. When you do this puff hardware you designed, were you worried about how much power does it consume or dissipate?
Thank you for your good question. Actually, we didn't change. I mean that we didn't use a new architecture of the path. It's something. It is proposed standard arbiter path, and we use that arbiter path. That it's a low power and the light overhead for the hardware. So just in order to make the approach resilient against machine learning, we applied that scrambling method that we use some bunch of the basic logic that control the communication between verifier and this arbiter path. And in overall, and we saw that our purpose method is still low power and it is feasible to use for the resource constraint IoT devices.
Okay, thank you. I had just one more small question. You tested and validated it for how many IoT nodes in your network?
Actually, we just implemented the point-to-point communication. But in overall, it is not a problem if we use this architecture for so many IoT devices. The only concern is that, for example, if someone is eavesdropping the communication line between verifier and prover, is it still able to model the communication traffic or no? That we tried with all of the available machine learning algorithm, and we saw that our method is resilient against modeling attack. But in overall, there isn't any limitation that if we check with that so many IoT devices in the real network.
Thank you so much for your work. Static malware analysis using ELF features for Linux-based IoT devices. The speaker or the authors of the contribution are Akshara Ravi, Vivek Chaturvedi from Indian Institute of Technology, Palakkad. And the paper will be presented by Akshara Ravi.
Greetings to all. Myself Akshara Ravi from Indian Institute of Technology, Palakkad. Today I am going to present my paper titled Static Malware Analysis Using ELF Features for Linux-based IoT Devices. This is an overview of my presentation. First, introduction. So, the malware has been a serious threat to the everyday life of humans since it impacts all sectors of the daily life such as banking, e-commerce, social media, and healthcare. There has been an exponential growth in malware in the recent years, registering over 450,000 new malicious samples per day, putting businesses and enterprises under constant threat. Adding to this, the computing systems are also evolving with a variety of computing systems available, such as laptops, desktop systems, servers, mobile phones, smart devices like smart TVs, smart watches, and cameras. But still, malware is an unsolved problem for all these computing systems. Many malware detection techniques were developed in order to safeguard these computer systems and servers from malware. The techniques involve commercial antivirus scanners, static, dynamic, and hybrid analysis techniques. Traditionally, the malware authors were interested in developing malware targeted for personal computers and servers. Therefore, most of the malware detection techniques were designed without considering constraints such as memory, power consumption, and network resources. However, Mirai-based DDoS attack was an eye-opener for the malware authors that IoT devices can be used as an effective attack vector targeting critical infrastructure. The Mirai malware caused the biggest distributed denial of service attack, which targeted the DIN domain name service servers and disabled major internet services such as Amazon, Twitter, and Netflix. As a result, a host of new malware using Mirai's leaked source code and targeting IoT devices have emerged, such as Satori, Reaper, Amnesia, and Masuta. These attacks exploit the inherent weaknesses of the IoT devices, like the lack of security design with open ports and default credentials. Mostly, the users will simply buy and install these IoT devices and don't change the default credentials or frequently search for patches. For them, as far as the device is doing its functionality, everything is fine. However, the IoT devices are now the weakest link in the network since the attackers target the vulnerabilities of these IoT devices and use it as a tool for carrying out their malicious intent. From the malware detection perspective, maintaining a huge virus database or setting up a sandbox environment which support the different platforms of the IoT malware is not feasible on a resource-constrained system. So the static analysis seems more effective here. Hence, for this work, we have focused on the static analysis of the ELF binaries collected at the Linux systems hosted by the IoT devices. Since almost 71.8% of these IoT devices use Linux as their operating system with distributions such as Raspbian, Ubuntu, and Debian. The main contributions of our proposed approach are: we proposed a malware detection framework for resource-constrained IoT network. We reduced the number of extracted features by applying chi-square feature selection. We reduced the time and memory consumption required for malware detection. We conducted experiments using 7 machine learning models by simulating a resource-constrained setup in a virtual machine. Our approach achieved an accuracy of around 99% in a short period of time compared to the state-of-the-art works. Now, coming to the literature review, today I am going to discuss only the works which are closely related to ours in the interest of time. First is the ELF miner framework by Shehzad et al. Here, authors do a forensic analysis of ELF files using 383 features extracted from the ELF header and analyze the classification potential of these features. Next, Van et al. Proposed approaches to detect and classify the executables using byte sequences at the entry point. Tian et al. Proposed a framework that can analyze the IoT malware using ELF and opcode features. Next, Go et al. Presented a survey on the state-of-the-art static IoT malware detection methods. Lee et al. Proposed that printable strings can be used as an effective cross-platform feature to identify IoT malware on different IoT platforms. Kumar et al. Proposed EDIMA, a distributed modular solution for detecting the IoT malware network activity in large-scale networks during the scanning or infecting phase rather than during an attack. Now, the proposed methodology. Here is the block diagram of the proposed framework. First, we will discuss the feature selection phase. Our proposed framework extract static features from the ELF executables and classify them as benign or malicious. From the set of features extracted, we eliminated those features which have 0, constant, null, or garbage value throughout the data set. Finally, we extracted 342 features, but not all these features are important in discriminating between malware and binainware. Also, since the proposed framework is aimed at resource-constrained systems, we need to reduce the time taken for detection. That is, we should reduce the number of features extracted. Hence, we tried different feature selection algorithms like information gain and chi-square on our dataset. Since chi-square performed better, we gave the extracted 342 features of all the samples to the chi-square feature selection algorithm. Output is the 342 features ranked according to their importance in determining the class label. Then we set different threshold for the chi-square statistic empirically and kept only the features having value higher than the threshold. Then these set of features were then fed to the 7 machine learning models like J48, JRIP, PART, Random Forest, Naive, Logistic, and Rider. We also checked whether the accuracy is reduced considerably. If not, we continue changing the threshold and reducing the number of features like 151, 121, 83, 50, and finally 34, which have the highest chi-square statistics. By doing like this, we were able to select 34 features which can predict the maliciousness of the given executable in comparably less time and with high accuracy. In the detection phase, from the unknown ELF executable, 34 features are extracted and given to the 7 machine learning models which classify the given executable as malware or binainware. The 34 features used in our approach are given in this table. Now, I would like to give a brief overview of the chi-square feature selection method. The chi-square is used to determine the amount of dependence between a feature and a class label. It is based on comparing the obtained value of the frequency of the class because of the split to the expected value of the frequency of the class. The chi-square score with the C class and I number of intervals is defined as chi-square is equal to sigma I is equal to 1 to C, sigma j is equal to 1 to I, Nij minus Eij the whole square divided by Eij. Here Nij is the observed value, that is the number of samples within the jth interval. Here we can assume it as the number of samples having a particular value for the jth feature belonging to the Ci class. Eij is the expected frequency of Nij and is given by Eij is equal to Mij into mod Ci divided by N. Here Mij is the number of samples having that particular value for the jth feature, and mod Ci gives the total number of samples belonging to the class Ci, and N is the number of samples. When two features are independent, the observed value will be close to the expected value and thus will have a smaller chi-square value. Therefore, a high value of the chi-square will indicate that the feature is more dependent on the class label. Hence, the features with a high chi-square value should be used for training the model. This table shows the reduction in the number of features when the threshold of the chi-square statistic is varied from 1000 to 3196. First, the threshold is set at 1000 and all the features having value from 1000 to 3196 were selected. Then we changed the threshold to 2000, 3000, 3190, and finally the 34 features which have the highest chi-square statistic value, that is 3196, were selected. Now I will discuss the experiment and results. First, the experimental setup. We did our experiments using the real-world malware data set from Virus Share Malware repository, which consists of 1,773 samples and used 1,426 benign samples from the Linux directories. Training of the machine learning models were conducted on an Ubuntu 20.10 operating system with 4 GB RAM and 200 GB storage. 342 features are extracted from the ELF executables using PyELF tools Python library. Then we have used the feature selection algorithm chi-squared attribute eval with the Ranger search method in Weka 3.6 toolkit. We have used the standard implementation of the 7 machine learning models in Weka. Classification of an unknown executable into benign or malware was conducted on a resource-constrained setup with Ubuntu 20.10 operating system with 1 GB RAM and 20 GB storage. This configuration was used to mimic a relatively small gateway device such as Raspberry Pi. This table shows the performance metrics of the 7 classification models for each set of features. As we can see from the table, even after reducing the number of features to 34, the models J48, JRIP, PART, Random Forest, Logistic, and Rider were able to achieve around 99% accuracy. And the only exception here is the naive Bayes, which got an accuracy of 97.81%. Also, the models JRIP, Random Forest, and the Logistic achieved the highest accuracy of 99.69 with 0.005 false positive rate and 0.002 false negative rate. This proves the fact that the chi-square was able to capture only those features that are significantly important in predicting the class label. Now, this table shows the time taken in seconds to train the model for each set of features. Consider the case of the JRIP classifier. Here with the 151 features, the time taken was 0.37 seconds. When the number of features was reduced to 34, the time was reduced to 0.12 seconds, that is a reduction of 0.25 seconds. This value is important for resource-constrained devices. Now, Let's consider the overall time and memory consumption. The feature extraction and pre-processing time per instance are 44.9 milliseconds and 0.16 milliseconds respectively. And extracting the 34 features from the unknown executable and prediction took approximately 20 seconds, and the memory consumption was around 12 MB. Now, I would like to compare the accuracy of our approach to state-of-the-art, particularly the ELF Miner framework, which is one of the prominent works which use the ELF header features. The ELF Miner was proposed for computer systems running Linux operating system, whereas our proposed approach focuses on resource-constrained systems running Linux operating system. So this table shows the accuracy of both the works. Even after reducing the number of features to 34, our proposed methodology achieved a comparable accuracy of 99% with a bigger data set. Finally, I would like to conclude my presentation. So, we have introduced a malware detection framework for resource-constrained systems such as IoT devices running Linux operating system. We applied chi-square feature selection algorithm to determine the 34 features which are more significant for prediction. Our approach achieved more than 99% accuracy with less than 0.1% false positive rate and false negative rate for all the 7 classification models with approximately 3,196 samples. That's all from my end. Thank you and have a nice day.
Yeah, thank you, Akshara, for a very wonderful work which you have done. I was just thinking, can we apply this kind of a framework on a system which is implemented on a chip?
Actually, now we have implemented a software approach only, software simulation only. So we are now trying to implement how this can be done on IoT devices. And chip also, since it have very less resources, so we are trying to implement on a hardware like chip. First, we will try it on an IoT device, and then we will progress our work towards chip as well.
Thank you. Thank you. Wonderful insight, and I wish you all the best for your future work. Thank you, Akshara.
Thank you.
The next paper in the session is Heap Safe, Securing Unprotected Heaps in RISC-V Processor. The authors for the work are Ashmit Dey and Sarup Ghosh from Pennsylvania State University. So I invite them to present their paper.
Hello everyone, I'm Asmit and I'll be presenting my research HeapSafe, Securing Unprotected Heaps in RISC-V SoCs. RISC-V is a promising new architecture that has gained momentum for its open platform. RISC-V based SoCs rely on a distributed development pipeline and can be prone to security challenges throughout its lifecycle, from design through use post-market deployment. In this work, I will demonstrate hardware security design strategies for mitigating heap memory corruption vulnerabilities in RISC-V platforms. There has been an exponential growth in the number of low-power embedded devices in the past decade. Most of these devices are resource-constrained and operate within limited performance budget, and hence the security of such devices are often implemented as an afterthought. Traditional security solutions implemented on such systems can become expensive due to the limited resources. These devices use embedded system-on-chip components. SoCs are a complete computing system implemented on a single chip containing logic, memory, and other peripheral components. One such SoC architecture that has gained recent popularity is RISC-V. It is an open source architecture which is customizable and extensible and is well suited for such embedded SoCs. An SoC core complex can have multiple cores with their own L1 caches, tightly integrated memories, etc. Outside the core complex, there are memory controllers like DDR3, 4 for communicating with the external memories, and some other peripheral controllers like SPI, I2C, etc. Point to note is that these peripheral devices can be mapped to a single large address space on the SoC subsystem to reduce the design complexity. This is critical as without proper isolation and protection in the address space, this can result in memory corruption vulnerabilities. Buffer overflow is a very common vulnerability, mostly present in low-level languages. This is because languages such as C provide free access to memory and hence lacks bounds checking. In the address space, buffer overflows can happen on the stack as well as on the heap. While overflows on the stack are somewhat easy to detect, overflows on the heap are a little bit more complex. Heap is used for dynamic memory allocation. A heap buffer is a memory space that is dynamically allocated on the process's heap using functions like malloc. The function returns the memory address of the first byte of the allocated space and is used as a pointer to the heap. Data is written to heaps allocated bytes with the pointer using functions such as memcopy, stringcopy, etc. Here we have a simple code demonstrating a buffer overflow vulnerability on the heap. The function accepts a data string from the user. A buffer of size 32 bytes is allocated on the process's heap. The input string is then copied to the buffer. Here, it is easy to overflow the buffer if the size of the string is more than 32 bytes. This can potentially overwrite process data on the heap in other allocated buffers and may lead to memory exploits. Another vulnerability that can occur on the heap is the use after free. This vulnerability occurs when the heap memory is reallocated after the data on the heap is freed. A previously leftover reference known as a dangling pointer to that memory can potentially access newly created data from that heap location. In this diagram, P3 is allocated at the same location where P1 was initially referenced. Now, even though the memory referred to by P1 was freed, it is still pointing to the same location as the newly allocated P3. Hence, P1 can be used to access, read or write data at P3's memory. This example code demonstrates a similar vulnerability. We allocate a buffer at P1. In case of an error, the memory at P1 gets freed. Now, it is entirely possible that when the memory referred to by P2 is created, it is at the same location as P1. In such a situation, referring to P1 later in the code can leak or even corrupt data at that location. To mitigate such attacks, we design HeapSafe, a hardware-assisted heap protection engine built as a custom coprocessor module on the Rocketchip SoC generator. For those who are unfamiliar with Rocketchip, it's an open source platform developed by the folks at UC Berkeley for generating custom RISC-V SoCs in a parameterized manner without having to write a single line of Verilog. You can design the SoC using Chisel, a hardware construction language based on the Scala functional programming paradigms, and compile the design down to Verilog. Rocketchip has a Scalar core, which is connected to a Rocket custom coprocessor, which is completely customizable. There are support for custom instructions that can be sent to the ROCC, which has an instruction layout like this. We specifically wanted to implement our security design on the ROCC because it's decoupled from the core pipeline. The coprocessor can be customized and tuned according to our needs during the SoC generation process, and that provides a huge benefit. We can drop in this ROCC module, scale up or down without worrying about the core. It is flexible to be interfaced with any RISC-V core IP implementing the RockIO interface. In HeapSafe, we aim to protect dynamically allocated buffers on the heap that are accessed using pointers derived from the allocation pointer. We enable metadata propagation between the pointers, and the system is able to trace the correct metadata for the pointer operations. HeapSafe is able to protect against buffer overflow on the heap and also prevent inadvertent use after free accesses. any program targeted for the RISC-V system can be updated to use the safe heap functions from the heapsafe library. Each pointer used to allocate a heap buffer will be converted to a safe pointer by the heapsafe library using a tag. Any other pointers derived from the safe pointer is also tagged as a safe pointer. The heapsafe hardware provides the metadata storage for pointers and validation during buffer write or copy operations. Let us first look at the details of the heapsafe library, and then we'll look at the hardware implementation. The safe malloc function allocates a buffer in the process's heap similar to malloc. The allocated memory is referred to by the address of the first byte of the heap called the raw pointer. We create a safe pointer from the raw pointer by encoding the topmost significant byte as a tag reference. Since we're using 1 byte to represent the tag, we can use heapsafe for a maximum of 255 simultaneous heap allocations in the process. We exclude tag 0 to maintain compatibility with the pointers that are not using the heapsafe engine. This allocation scheme is sufficient for standard embedded RISC-V applications running bare metal. However, even though we have used 1 byte to represent the tag, this bit allocation is customizable in the library. When compiling the heapsafe library, this bit allocation for the tag can be set as required to match the heapsafe hardware. These are the cases where we ensure tag propagation. When allocating a heap buffer, a new tag is generated. The safe pointer is created using the tag and the base pointer. During a pointer assignment, the tag from the original safe pointer is propagated to the new safe pointer alongside the raw pointer value. During a pointer arithmetic operation, such as an array access at a specific index, the new safe pointer created by adding or subtracting the offset receives the same tag as the original safe pointer. When a safe pointer is cast to a new type, the tag is propagated to the safe pointer of the new type. Two other cases that need special mention are the null pointer and the manual pointer creation from literal values. In both of these cases, the tag is set to 0. The tag 0 also indicates that the pointer is not protected, and any safe heap operations using the heapsafe library will result in an error. The safe copy function enables a safe copy operation from a source buffer to the destination buffer, which guarantees that the buffer will not be overflowed. To perform the copy operation, we check the pointer being used to refer to the destination heap buffer. We send the pointer with the hsValidate instruction to the heapsafe engine to perform an out-of-bounds validation. The safe free function is complementary to the safe malloc, which allows a clean deallocation of the memory space and metadata removal from the heapsafe engine. We send the safe pointer to the heapsafe engine with the hsFree instruction to perform the metadata removal. We can then use a raw pointer to free the memory. By repurposing the MSB bits of the original pointer to store the tag, we get the benefit of easy tag propagation. However, the safe pointer by itself is not a valid memory address due to the inclusion of the tag bits. So if we try to re-reference it normally, it will fail and raise an exception. The safe read-write functions can safely extract the raw pointer from the safe pointer. It sends the hsValidate instruction to the heapsafe engine to validate the read-write access, and then performs a dereferencing to read-write data in memory based on the raw pointer. The heapsafe engine is a custom-designed accelerator on the Rocket Custom coprocessor. It consists of a metadata parser, a metadata table, and a validation engine. The custom heapsafe instruction for storing the metadata is hsStore. The metadata parser extracts the tag, the raw pointer, which is the base value, and the size of the memory. We pre-calculate the bounds address to improve performance during validation checks. This is because the store instruction is non-blocking, while the validation can be performed in a synchronous manner. We populate the fields tag, base, bounds, and set the valid bit to 1. For out-of-bounds validation on a pointer using hsValidate, we extract the raw pointer and the tag, and based on the tag, we look up the bounds information from the metadata table. We then perform a bounds validation and send a response back to the core. For hsFree, we extract the tag and just set the corresponding valid bit in the metadata table to 0, and that indicates that the entry is no longer valid and can be overwritten. This code demonstrates the usage of heap-safe in C programs. Let us consider a function that receives a lowercase string data, converts each character to uppercase, and stores to a buffer allocated on the heap. If we wish to protect this upper buffer from overflow, we can replace the code with its heap-safe equivalents. We replace malloc with safe malloc, so this upper becomes a safe pointer. Now we can no longer use the standard dereferencing for upper, so we replace that with the safe write function. Now I've mentioned that these ROCC modules can be easily customized. This is a Scala configuration class for generating the heap-safe hardware. Build ROCC is the trigger that generates our heap-safe engine, and this n parameter specifies the number of heap-safe modules we want to actually instantiate. And for each of those instantiations, we can specify certain parameters, such as the set of custom instructions we want to use, the size of our metadata table that we want, and the hardware thread to attach this heap-safe module to. We evaluated heap-safe performance by running a simulated microbenchmark. We generated some stack buffer operations and heap buffer operations and swept their percentages. We ran 4 versions of the code: a baseline without any protection, softBC, software low-fat pointer approach, and heap-safe. We also had a non-blocking version of heap-safe where the validation was performed asynchronously. We swept the workload balance between the stack and the heap and evaluated the trend. At less heap operations, but the performance of heap-safe and softBC were fairly close. However, at higher heap workloads, around 75%, we saw a noticeable execution time improvement of around 20%. The non-blocking version was even better, with a 38% improvement over softBC. The area overhead for the heap-safe module was 1.59% based on an RTL synthesis for an RT300 FPGA. On the standard RISC-V tests benchmarks, we see a 1.5x overhead over the baseline, which was still 22% faster than softBC. So that brings us to the end of my talk, and thanks for listening.
Thank you, Ashmit. Just because of the paucity of time, I'll have just one quick question to you. How much was the hardware overhead over the base and the coprocessor?
Right, so that's hardware overhead. I'm assuming you're asking about the area, right? Like how much bitstream, extra bitstream it generated?
In terms of number of gates or in
yeah, I don't, so based on the bitstream evaluation, so that's what we have, like 1.5% over a baseline Rocket chip. So a Rocket chip without any coprocessor and Rocket chip with implementing our heap-safe coprocessor, it increases by 1.59%. Yeah.
Thank you, Ashmit.
Yep.
So authors are Abdul Rahman, Aritra Dasgupta, Mohammad Moshir Rahman, and Saroop Bhunia from the University of Florida. I invite them to present their paper.
Hello everyone, welcome to my talk. My name is Abdul Rahman Al-Akil. I am from the University of Florida and I would like to present SEVA, a structural analysis-based attack on sequential logic locking. As a brief introduction to our talk, we all know that system-on-chip lifecycle has a multiple stage process, starting from design spec, going all the way to the deployment or to the customer. And we all know that in each of these steps there are multiple of complex processes that need to be done in order to design, develop, and test these systems. Although the mentioned process is very beneficial in terms of saving cost and time to market, it is risky and there are many trust issues that might actually occur during the life cycle of the electronic system. Some of these threats can actually range from backdoor insertion to counterfeits and overproduction and even modification of the IPs and side channel analysis. Therefore, there are a number of techniques that are designed and developed to protect IPs and hardware systems against these threats and attacks. Techniques such as state space obfuscation, logic locking or logic encryption, and camouflaging can actually help prevent some of these attacks and detect any malicious activity. In this talk, we will be focusing on logic locking or logic encryption, which is a technique that locks the gate level or the RTL hardware IP and requires a key in order for the functionality to be restored. And there are many different techniques that have been proposed in the literature, ranging from simple random key insertion up to some more advanced techniques such as SFLL and crosslock. However, as many of these techniques have emerged, there are also attacks that are aiming to restore the functionality and break these protections. One of the most popular ones is SAT attack, which uses SAT solvers to reduce the key search space and remove some of the key classes in order to get the correct key. So as we can see here, there are a number of attacks and there are a number of locking techniques that can actually prevent or countermeasure these attacks. On the other hand, state space obfuscation is actually using a sequential type of locking, which means that the functionality of the IP that is locked is not really available until you provide a sequence of keys through the primary inputs of that IP. So basically, once you apply this specific sequence, you can reach the enable state or the normal mode. Otherwise, if you make any mistake during this key sequence, you will go through the obfuscated mode and you will be locked with randomized or rubbish output for that IP. So if we dig deeper into the sequential locking mechanism, we realize that in order for us to actually implement this technique, we have to add more state elements or registers that have to occupy and define these locked and unlocked modes. So these registers will also drive some modification cells that control the correctness of the output depending on which mode we are in. So if you are in the correct mode, then these modification cells will not affect the functionality. If we are in the locked mode or the obfuscation mode, then we will see randomization and corruption in the output. So if we think about this, we actually realize that obfuscation or state space obfuscation is actually a way of locking the design without introducing new primary inputs that are dedicated for the key. And this is really promising because you can still use the exact same set of inputs as your key input, and then once you enable the design, you actually use the IP as normal. But the problem here is that the structural changes that are introduced after obfuscating an IP will be deterministic and can be easily located and attacked. And this is what motivates this paper or this work. We are trying to evaluate the level of security of existing locking schemes that focus on state space locking. And in order for us to achieve this, we present SEVA, which is a structural analysis based attack that evaluates the security of sequential based locking. So the goal of this attack is to basically analyze all the registers in an IP and label them as either added state elements that are part of the locking mechanism, or normal state elements that are part of the original functionality. So if the attack is actually successful, then we will highlight all these red registers that are shown in this figure. And in order for us to do that, we analyze the fan-in cones of each register. So what we do is we extract a subcircuit of each register, and that is the fan-in cone, and we use that as our main piece of information to actually determine if this state element is either added by the locking mechanism or part of the original functionality. So once we extract these subcircuits, we actually extract a number of features from each subcircuit that defines these circuits or these fan-in cones. So we can generate this feature matrix, and we call it F. And what it does is it lists all the extracted subcircuits or cones, and then it lays out all relevant features that represent this cone. And these features can be the number of BDD branches, the number of edges in that subcircuit, the number of AND gates, and many others. And once we have this matrix, we can actually use it to identify which of these cones relate to the added state elements. So the overall attack process is basically to start by analyzing the structure of the locked IP. Then we extract subcircuits from each register, which are the fan-in cones, and then we extract all the relevant features from these fan-in cones, and we generate the feature matrix. After we generate the feature matrix, we have two paths. We can go with mode A or mode B. So mode A is the supervised analysis process, and mode B is unsupervised. And in both cases, we reach a proximity-based cluster refinement, and in this stage, we try to reduce the false positives by correctly labeling the added state elements. And finally, we remove the added or the correctly identified state elements in order for us to transform the locking scheme from a sequential one to a combinational one. So we actually have two attack modes that are supported by this tool, and both of them use a set of classification algorithms, and we can classify them as mode A, which focuses on supervised based learning, and mode B that does not really need any learning, and it just does clustering. And both modes are actually beneficial in different techniques. So if we have access to the locking mechanism and the locking algorithm, we can easily use mode A, since we can generate training data. But even if we can't, we can still use mode B, which is a bit less accurate, but it's still good enough, and it can give us good labeling accuracy even without any training data. And after that, we also go through an error correction and proximity analysis, and basically we try to analyze a set of correctly identified added state elements, and then we structurally look for surrounding and neighboring registers, and we usually identify those as added to if the features are correlated with the correctly identified ones. So in order for us to demonstrate the potency of this attack, we actually apply it on Harpoon, which is the most famous sequential locking technique, and we used a set of SCAS89 benchmarks and open source files from the MIT CEP functions, and there are a number of different styles of IPs that we have dealt with and different sizes, just to show the scalability of the attack and the level of accuracy across practical and commercial sized IPs. So if we look at the accuracy results, we have performed the locking schemes that we mentioned, which is Harpoon, in 3 different modes or 3 different settings, where the overhead is fixed at 25%, 50%, and 100%. Although these are not realistic, we needed to apply different styles and different sizes of locking in order for us to explore the accuracy across different levels of locking. So basically both mode A and mode B have been applied to the locked designs, the locked IPs, and in both cases we got really high accuracy. So we got an average of 97% accuracy when labeling the added flip-flops or the added state elements, and the false positive and false negatives are not really that high. They're about 1 or 2% in most cases, and this shows that this attack can actually get really close to identifying all added elements that are related to the sequential locking techniques. So in order for us to understand the impact of the level of accuracy of the attack, we can analyze the search space or the key search space of the locked IPs before and after the identification that we do through our tool. And basically, before we do any labeling to the added registers, the brute force complexity is what's shown on the left column, but then after we identify the added flip-flops, the brute force complexity is reduced to the one which is the SQ column. So basically you can see that the significant reduction in the search space shows that this attack is really impactful, and it is still hard to brute force, but we can also apply different attacks and different techniques after this reduction in order for us to completely unlock the IPs and restore the functionality. One more thing here is that when we transform the locked IP from the KY or the left column to the right column, we actually transform it from sequential based locking to combinational based locking, which means that we have a plethora of attacks and evaluation techniques that can actually help us determine what the correct key is and how to fully unlock the IP. So in conclusion, we have presented a novel technique that is structure based. It doesn't require any prior knowledge to the functionality of the design. It is really scalable, and it is quick to extract and label the registers, and it's focusing on sequential based locking. And this is interesting to us because sequential locking techniques are not properly analyzed and evaluated in terms of security. That's why we need more tools and more algorithms that will help us measure and quantify the level of security of any sequential based locking technique. So we also presented a proximity refinement step, and this step can actually help us remove some of the false positives and determine whether the identified added flip-flop is either correctly identified or not. So future work can relate to trying to fully unlock an IP, so adding a step after this, which might include functional or structural analysis on the IP in order for us to fully unlock the IP and restore the functionality. Thank you very much for listening, and please let me know if you have